All right, now let's talk a bit about signal processing. So we've talked already a bit about what options we have to get data about the environment, but in almost all cases, this data is in the form of a so-called time series. So along the x-axis, we have time progressing in more or less equal intervals. And along the y-axis, we have whatever measurement we can make. And the data we get is, in almost all cases, somehow noisy. So we have the, so to say, the true signal in blue, and then we have the actual measurements we get in green, which contain additional noise that we're not actually interested in. At a very fundamental level, if you look at measurements in general, then we have two types of noise. We don't want either one, but the one is the so-called process noise. That means if I hold my mobile phone in the hand and try to keep it still, then just because of my muscles and my heartbeat and so on, the mobile device will still vibrate a little bit. This is so-called process noise. It's not something we want to measure, but it's physically present in the motion of the mobile device, for example. And on the other hand, we have so-called measurement noise, which is not actually physical movement in this case that we're measuring, but it's basically just thermal inaccuracies that are created in the sensor itself. So, for example, if it heats up, then we have more molecular motion of the individual components, and that will increase the noise that we're measuring also, even though it has a different cause. And in both cases, we're not interested in the noise itself. We want to remove that. Sometimes we might be interested in how much noise there is. So we want to know the magnitude of the noise component in addition to the actual signal, because that might help us make more accurate predictions. The big problem is both types of noise are part of the so-called hidden state. And for this, I want to talk a bit more about the so-called noise model. This is here based on the Kalman filter. This is a very common signal processing approach that is used for all sorts of sensor data. So you can, for example, use it for IMU data. Originally, it was designed in the 50s, I think, for radar data from airplanes, but it applies to just about any type of sensor data. And so the idea behind the Kalman filter is that here in the center, this value x is the true state of the system, let's say the true acceleration value of our device that we want to measure. And we have a so-called transfer function. This is a, which takes us from one time step to the next. So in between two time steps, the old system state is transferred through that function a into the new system state. We also have this control function. So this is something we can actually control. We have influence over. And through some function b, this also influences the state of the function, the state of the system in the next step. Then we have the process noise, which is actually like physically present motion, for example, that however we don't actually want to measure. And then we have the actual measurement happening, which is again a function that translates the actual real state of the system into whatever measurement we actually can see at the end. So a very simple example, let's say we're talking about acceleration, then the IMU in a mobile device usually has a maximum value of acceleration that it can sense. Let's say that's 2g, 2 times gravity acceleration. And if I move my device faster than 2g, then the value will just be clipped. So the maximum is 2g and it will stay there. That means this function h here introduces, for example, this clipping into the actual measurement that I get to see. So I only see a value of exactly 2g, even though the actual acceleration is higher. And in addition to that transfer or measurement function, we also have then the measurement noise itself. That's basically added on top of whatever transfer is happening from the true value to the measured value. And in between each of these measurements, then we have kind of the time step or time slice, which is here given by the parameter k. And on top of these two different types of noise, the process noise and the measurement noise, we also have a covariance function, Q and R, for each of these, which isn't something I want to go into too much detail right now, but these basically tell you how large the noise is in each dimension and how much noise it will add basically on average. All right, so this is the so-called noise model, and as you can see, a lot of things inside here are actually hidden from the system. So they can't really be known, they can only be observed through these measurements here and maybe influenced through these control vectors U that we have. But almost all of the data below this line is not directly visible to, or cannot directly be measured, it can only be inferred. All right, now let's look at how do we actually get rid of the noise, or at least reduce it. So a really, really simple approach is to use a so-called filter kernel. This filter kernel here is the blue function. So here it's just a very simple step function or square function. And when I multiply that on top of my measurement data, then the result is a so-called moving average, basically. And I'm removing at least part of the noise. So let's say my true function here is the green one, and the red one is the actual measurement values with noise. Then when I multiply that step function on top of my red measurement values, the result is the cyan function that's already, again, quite close to the original sine wave. One thing that's not quite as apparent here in this image, you have to look closely, is that the peaks of the resulting functions are shifted a bit with respect to the true function. So using this kind of moving average, even though it's very simple, it will introduce a time delay. And if you need to react very quickly to specific events, then it's maybe not the ideal filter for that scenario. From a mathematical point of view, this is so-called convolution. So it's basically just a point-by-point multiplication of two functions. And the two functions here are the noisy red measurement data and the blue step function. And the result is, as I mentioned, that cyan filtered function that's less noisy, but also somewhat time shifted with respect to the original function. One other simple approach to characterize signals is to take a time window of a bit of history of the signal, and then just calculate the mean and the standard deviation for that time window. So standard deviation or standard error can be very roughly approximated that this is kind of the average difference from the mean value. The problem is this is a very one-dimensional look at things. So the standard deviation tells you a bit about how much noise there is in the data, but you can have very different signals that have the same mean and standard deviation, even though they actually look quite different. They can map to the same values. So here's a brief example. I also can recommend this book if you want to go into a bit more detail on signal processing. This is like a free web book, basically, that you can look through. And here, as an example, you have two signals where the mean is changing and the standard deviation for each of these windows is changing. And here you have a signal where the mean is changing, but the standard deviation is remaining constant. And if you look at, for example, this window from 320 samples, then within that window, the signals look very similar. But if you look at the bigger picture, then you can see that they're actually quite different. And that up to a certain point, you can capture this with a larger window. But the larger your time window is, the longer your delay will also be. So again, this only works if you don't need to react quickly to changes in the signal. One other very, very helpful bit of signal processing is the so-called Fourier transformation. This is also often called the FFT, fast Fourier transformation, or DFT, discrete Fourier transformation. So there's lots of libraries for that kind of do the math work for you. And the fundamental idea is that if we have this time series of data, which here is a nice sine wave, then we can represent this as a sum of pure sine waves. And this is usually called transporting the data from the time domain to the frequency domain. So both of these represent the same function, just here as a time domain function and here as a frequency domain function. And you can already see that the main frequency of that signal is probably 0.5 hertz. So one cycle every 2 seconds. The important thing is that this frequency domain representation is also just a function that you can then filter again, convolute, threshold, and so on. And some things are a lot easier to detect with this FFT transformed or Fourier transformed data than with the original data. So let's say we add again quite a bit of noise. Then we have the true signal here in blue and the actual measurement signal in green. And if we now take the FFT of the green signal, then the FFT, the frequency domain representation will get noisier, but it will still keep the rough original shape. So we will still have this peak here around 0.5. And now you can, for example, still do a threshold and just look at all peaks that are above 0.25, let's say, and still get more or less the same information about the signal than you did in the perfect case without noise. So a lot of things are easier to actually analyze when you look at the frequency domain transformation of a signal than when you look at the pure time series. All right, so much for signal processing. Now let's talk about the implications we have for our context detection. So one of the implications we can, if we actually know the context is that we can infer something about the attention level or the kind of the bandwidth between the device and the user that's available. So that means, can the user like look at the screen at the moment, or do they have to look someplace else? How much speed can they devote to inputting data? So can they type with 2 fingers, or can they just use one hand? How much time do they have available to interact? So can they just devote 5 minutes to a task, or can they only have 5 seconds? What kind of operations do I actually have to, or am I kind of allowed to perform? So is it maybe impossible that I can, so do I need at least one hand for another task? Do I need to keep quiet? Like, think of the example with the cinema, but there might even be like legal issues to think about. So one very low-tech example is when you visit, for example, a BMW factory, and I did that for a few projects during my PhD, for example. Then they would actually like put a sticker over your mobile phone camera to make sure that you can't take any pictures of secret prototype cars while you're on the within the factory area. And you could, of course, think about doing that in an automated way. So setting up kind of zones within your mobile phone camera will be automatically disabled. But once again, that kind of also goes both ways. So that would wouldn't be long probably until somebody, let's say, at somebody with malicious intent would then also get such a device and prevent people from taking pictures of things where it would actually be a good idea that you have pictures, let's say police brutality or whatever. So there's quite a number of implications when you try to automate some of these context aspects that I think should always be in the back of your head. So we already talked about this. So even for the driving scenario, for example, there's always a scenario also where you would actually want to use your mobile phone while on the steering wheel, for example, to make an emergency call. Or when you're in a crowd and your screen is automatically dimmed because it thinks you're in a cinema, there is definitely also another scenario where it makes sense to not do that. And so the important aspect is you have exceptions all the time, and these exceptions are probably even more important than the general case, but exactly because they are exceptional and therefore not as common, it's probably even more difficult to recognize the exception scenarios automatically, even if you would be able to detect the main scenario reliably, like the user is driving a car. Then you would still need to somehow have a way to turn off this feature to make an emergency call, for example. And that's even more difficult by, I don't know, how many orders of magnitude. All right, so thanks for listening again, and until the next video.